Thank you, Mark. So I will highlight two of our recent works that are related to applications. In this case, we realized knotted configurations, topological configurations in liquid crystals that stand in between crystalline solids and isotropic liquids. They have orientational order described by the director field. And we can have fluid liquid crystals made out of small molecules like the ones in here, as well as liquid crystal elastomers or soft liquid crystal solids, where we have cross-linked molecules, anisotropic molecules, like you can see in here. And in the first part, I would like to show how liquid crystal vortices can be used to steer light and also to localize light spatially. So in a liquid crystal medium, a polarized beam of laser light will experience effective refractive index. So if we have an extraordinary mode of light propagating within a liquid crystal, and we have such a vortex line perpendicular to the screen in here, in this geometry, the beams of light will be deflected because when traveling from point y1 to y1 prime, due to the Fermat principle, light will take the trajectory that gives the shortest amount of time to travel from one point to the other. And this gives us effectively this cone geometry that you can see depicted in here. We have the effective lensing of light by this vortex line. So this is just one example of vortex line with +1 winding number, but of course we can have many different ones realized in liquid crystals, and applying the same Fermat principle, the beams of light will be steered as depicted in here in this geometry. So these are all computer simulations where on top of the trajectories of numerical and moderate trajectories of light, we have this effective refractive index in this color scale that light will see. And what's very interesting is that this effective cone geometry of refractive index is giving us the focusing of light and steering of light, similar to that what was predicted in many works in the past for light steering by cosmological strings, cosmic strings. And so in that case, we have this cone geometry in space-time, and again, we would have very similar deflection of beams of light, or light propagating around the cosmic strings. So what's interesting is that if we would plot the deflection angle as a function of refractive index and isotropy divided by extraordinary refractive index versus this parameter here that gives us gravitational constant, speed of light, and the linear mass density of the cosmic string, we can see that the two models give the similar predictions up until pretty large values of optical anisotropy of liquid crystals. And liquid crystal vortices are actually much more powerful steers of light than not just cosmic strings, but that are still, as we know, elusive cosmological objects that are only now, being studied by gravitational wave experiments that are still somewhat elusive, right? But the deflection angles, for example, are much larger than what you would have for the strongest steers of light in cosmology, like quasars, for example. And so in liquid crystals, we can now pattern arrays of liquid crystal vortices by using photopatterning, where we have these other benzene dye molecules grafted on the surfaces of confining glass plates. And with polarized light, we can then direct the dye molecules, and with their help, also liquid crystal molecules, so that we can pattern arrays of vortices in liquid crystal. And you can see here such a crystal of liquid crystal vortices in the director field depicted by these lines, and these are experimental images between cross polarizers. And here you see these vortices that run perpendicular to the screen, and integer strength vortices, interestingly, tend to split into half integer ones to minimize elastic energy associated with them. So for every integer winding number vortex, we'll have 2 vortices in the bulk of liquid crystal. Now, as we send a laser beam of light, we can see it meandering in here between the vortices in this array. And the experimental traces are very closely consistent with computer simulated ones for different beams that you can see in here in different geometries. Interestingly, as we increase optical anisotropy to certain value, in this type of array of +1 and -1/2 vortices that we generated, we can localize the beam of light, but the optical anisotropy in this case has to be fairly large, so on the order of almost 0.4. However, if we pattern higher winding number vortices, so in this case it's +3, and half integer and also integer of negative sign into an array, as depicted in here and also experimentally imaged. In this case, the +3 vortices would split into a hexagon of half integer ones, as depicted in here in this geometry. And the beams of light, in this case, can be spatially localized or closed into loops, as depicted in here. So these are computer simulated results and also experimental results. So also beams of light can be deflected backwards in this geometry. And much more different, powerful steering and control of light propagation can be done. Moreover, this control can be extended to, expanded even further by using external stimuli. So, for example, the deflection angle of light due to its interaction with these vortices in the arrays can be controlled by applying electric field and effectively stretching these vortices, as you can see in here. And so by just changing applied voltage within a range of up to 3 volts, you can see we can steer beams in a very large range of steering angles. Also, we can use light itself to redirect liquid crystal director around these vortices and then change these deflection angles as well. Moreover, in a chiral liquid crystal where we can stabilize twist solitons that can be kept by vortex lines in here, the twist disclinations, we can form knots of these and localize laser beams of light into not just closed loops, but also knot structures as well. In yet another example that I would like to highlight, which is in collaboration with Jig Broad and Ching Liu and Jacques and also Darian, the 2 students working with us, we cross-linked liquid crystal molecules, polymerizable liquid crystal molecules into an elastomeric network. So in this case, we know that liquid crystal elastomers exhibit very interesting properties and are often thought about being used as artificial muscles, because by applying external stimuli like temperature, we can change order parameter and in that case, the orientational ordering is coupled with mechanical properties of these materials. And so the question in here is, could we somehow go beyond just uniformly aligned samples and use topology of complex structures like not solitons in order to control topography of surfaces of films? So in these types of films, we can, in a chiral liquid crystal elastomer with the composition that I was showing you earlier, we can realize the topological not solitons that are called Hopfians, in which case we have pre-images corresponding to single value of order parameter field, the liquid crystal director orientation. The pre-images are linked with each other. They have the shape of closed loops, and the linking number is geometric interpretation of the Hopf index. And so this is the type of topological soliton depicted in here in two orthogonal planes perpendicular to far-field director and containing far-field director. And for any pair of the order parameter values in the vectorized director field, we have the pre-images in the form of closed loops, which are linked with each other exactly the same number of times, in this case equal to 1, which corresponds to Hopf index equal to unity. And so these types of solitons can be realized experimentally, and we can verify that by doing three-dimensional nonlinear optical imaging. So you can see in here cross-sectional images for different polarizations of femtosecond laser light used in 3-photon absorption-based polarized 3D luminescence imaging. And we can see that theoretically or numerically modeled images very closely agree with the experimental counterparts. Moreover, as we would visualize the pre-images themselves based on when reconstructed from experiments of this kind, you know, the three-dimensional luminescence imaging, we can see that pre-images also not just up to topology, but also geometrically closely resemble the results of numerical modeling that's based on minimization of elastic free energy. So now in our three-dimensional topological soliton, we have all possible orientations of director, and for every single orientation of vectorized director, we have a pre-image with the shape of closed loop, and these pre-images tile themselves for every constant value of polar angle into tori, whereas the smaller tori nest inside of bigger tori all the way until the north pole of this S2 order parameter space of vectorized director field, where in its exterior the director is uniform and the interior are all possible orientations of director field. And so now, as such an object is localized within a film of liquid crystal with a uniform background, we can see in here the topographic change of the surface topography of the film, and we can see that by changing temperature in a large range of values, we can control topography of such a film, and that is consistent also between experiments and modeling. And so in here you can see a large array of such solitons in a liquid crystal, and as we change temperature, we can see that the topography can be controlled going from flat states to the one with holes and mountains depending on temperature of the film that we have. So in summary, I showed you that liquid crystal vortices can be used to control and localize laser beams of light, as well as topological solitons, not solitons, can be used to control topography of films when we embed them within the uniform background of aligned liquid crystal. Thank you.
Thank you, Ivan.